Project 1.3, a counting circuit. This project explores crucial elements of electronics, including oscillation, display, and input. This circuit also explores in-depth logic such as sequential logic and clock pulses. The first part of this circuit is the button input. This circuit uses the pull-up feature, which is located on the left side of this diagram. To show that the circuit is working, an LED is attached to the end of the 4011 logic gate. This is the truth table and diagram for a 4011 logic gate. It is a combinational logic chip. For this circuit, the chip operates the same way as the NOT gate, opposing any power that is in the input and producing the opposite output. In either input feature, when the switch is pressed, the current takes the path of least resistance to the inputs of the 4011. At rest, the pull-up feature has an LED that is on always, and the pull-down feature has an LED that is always off. There is a resistor in each circuit to create a path that has less resistance and also to prevent a short circuit from occurring. The NAND gate has an overall output lead that allows it to spit out any extra voltage. This allows for current to go through the LED and into the output lead of the NAND gate, but when the gate is producing power, the LED does not turn on because it cannot counterbalance the power. This is the breadboard prototype of both features. The green LED is on a pull-up feature and the red LED is on a pull-down feature. The next phase is creating oscillation. This is called the NAND gate oscillator, and there are two main features, RC1 in green and RC2 in red. The way RC1 works is that there are features that allow the button to be pressed once and for the circuit's function to be held for a certain amount of time depending on the capacitor. RC2 is used to create an oscillating effect. When it produces power, the capacitor spits out voltage, turning the NAND gate off, and it reduces the power in the capacitor, therefore turning the NAND gate's output back on because there is one input without power. This is an extended version of the NAND gate oscillator. There are videos on these circuits doing their effect, but they are linked in the description below. The third part of the circuit is a decade counter. All in all, this is just used to reduce the clock signal produced by the oscillation of the NAND gate oscillator, and that is done through the CO pin, otherwise known as the divide 10 pin with the yellow LED on it. This is done through logic gate 4017. It divides sequentially the clock pulses created by the NAND gate oscillator and uses the carryout clock pulse for the rest of the circuit. The fourth part converts the clock pulses from the divide 10 pin into binary values between 1 and 10, otherwise known as 0000 and 1001. These are done through the 4 LEDs, and they show a binary value equivalent to their digit placement. This is done through the chip 4510, which displays single-digit numbers only. There is a 4516 chip that does the same effect, but it can display numbers between 0 and 15. The chip can count the clock pulses up and down depending on whether or not the up-down lead is either connected to power or connected to ground. Each LED is given a value on the binary scale depending on their digit placement. 0001, 0010, 0100, and 1000. These are nibbles. This is the table of all the binary values used in this circuit, both the prototype and the final circuit. The first 10 are used in the final circuit only, and all of them are used in the prototype, and they have been corresponded to their appropriate LED as shown in the diagram previously. The fifth step is logic gate 4511. This is used to convert the clock pulses from the binary values of the 4510 gate only and convert them into numerical values that can be displayed on the 7-segment display. This can be seen as both a sequential or a combinational logic chip just because of how many subcircuits are within it. With the exception of the 4511, all the other logic chips are internally resisted, so they can have LEDs placed on them directly. However, this one is not, so there are resistors between this and the final 7-segment display. The final step is the 7-segment display. This is used to display a single number, a single-digit number. This is placed at the end and is considered to be 7 individual LEDs and takes its inputs from the 4511 logic gate. Respectively, the inputs of the 7-segment display and the outputs of the 4511 logic gate are the same. This is a truth table for the 7-segment display. If it has an H, it needs to be a high input in order to produce the number. If it's an L, it's a low. Thank you for listening.